I'm standing in the engine bay today as the measurement report for the engine of this car has now come in. So it's been completely stripped, taken apart and measured thoroughly. The block's been acid dipped, so I'm off to Classic Engine Workshop over in Worcestershire today to see how things have gone. Hey Roger, how you doing? Good to see you again. Yeah, very well, thanks. So, whereabouts is Audrey?
Well, I've come through into the clean room, we'll have a look.
Excellent, cheers.
Okay, come through.
Right, so it looks as though you've got a load going on here at the moment, and it's quite difficult to tell which one's which. Everything from your Lancia engine there, there's a Porsche engine up there.
Yeah.
What have we got down here?
This is an Aston V8, so the 70s, 80s Aston V8.
Nice.
So we're doing a couple of those at the moment for different customers, including a high performance version. We've developed some interesting things, ported heads, CNC ports actually that we've had computer designed with matching camshafts and whole kit for a performance upgrade.
That is a big lump of aluminium.
It's a chunk, isn't it?
Yeah.
We've actually developed, there's a block down here that you can see that's got our new 6 litre conversion in it. So it takes it from a standard 5.3 or 5.7 for the Vantage up to a 6 litre.
So I got taken out in the DBS V8
that's
about 25
exactly,
years ago, and at the time the fastest car in the world, 170 miles an hour, and it was an amazing experience.
Well, this is exactly what that's from. I think they also put this engine in the William Towns Lagonda, the super wedgie.
Super wedge.
The super wedge, which is a wonderful thing. Glorious engine, Tadek Merrick design.
Oh yes, I remember reading about that. Yeah, okay. And then here we've got Mercedes.
This is a Pagoda, so the 280S. This one happens to be a 280 SL, which is the 7 bearing crank. They also do the 230, which is a smaller capacity, with a 4 bearing crank. But they're all very similar architecturally speaking. And actually, the history of this engine goes back to the prior model, so the 190 SL. It's a 4-cylinder version of this essentially.
Oh, okay.
And the 300 SL. It's a very similar design to the Datsun, the later Datsun 240, 260, 280.
I was going to say that camper looks very familiar.
And in actual fact, my understanding is that Datsun bought the rights for this engine from Mercedes. So it went on to have a very long and venerable life, much like the XK that you've come to talk about today.
So the reason I've come here today is Roger's stripped down everything, and the block's just back from acid dipping, and he's done a full measurement report. And obviously one of the key things is about this, it's kind of resetting the whole engine, isn't it? It's kind of getting it more than factory fresh.
That's right.
Rather than just a rebuild.
Yeah.
And so with all of that, I think, do you want to take me through the process?
Sure, let's have a look. So the whole ethos of what we do at Classic Engine Workshop really is based around restoring the engine in order to match any kind of restoration to the vehicle as well. So if you're restoring the car, you want to have the perfect engine. It's going back to factory condition, or maybe you're having some performance enhancements or whatever it might be. Yeah. But it all has to be done properly. We're not in the game really of making something work again, just fixing stuff. We're here to restore stuff and make it match the highest standards of restorers.
Yeah. But based on the engines I've seen from you, I need to do a good job on the car.
I think so, yeah. Yes, very rarely. I mean, 90% of our work is with professional restorers rather than individual customers. So, the whole point about that is that it's a broad standard across the restoration industry. If you're working with proper professional restorers, that they will be pushing towards that quality of finish and the level of factory finish, or even better in some cases, if that's what the customer's looking for. Yeah. Now, in the case of all of our engines, we do have several XK engines on the go at once, so we've got 3 or 4 in at any one time. And so what we have to do with all of our engines is make sure that we have a way of identifying and tracking them.
Yes.
So for all of our engines, we create what we call our birth certificate. This is what we have for all of our engines. We name all of our engines after something. At the moment we're going A to Z of racing drivers, but in the case of your car, we've already got a name on the car, so we take that.
Yeah, so my brother named it after Audrey Hepburn, the other 1960s icon.
We don't like to put customers' names on stuff as we send them away to machine shops and so forth, So we just put a reference name. Essentially, it describes the engine a little bit. It takes a photo from 4 sides so that we can recognise what came in with it, what was attached to it when it arrived, and what the condition was when it arrived. Because if we need to talk to a customer about what's missing, for instance, what are you doing about your alternator? What are you doing? I can see it came in without a water pump, for instance. So what are we doing about the water pump? Would you like us to obtain one? All that kind of stuff. So those are the kind of conversations it helps to have that. And then with our team, we log in and out, we clock in and out of the projects.
Oh, right.
And that's what the QR code is for. It's for our clocking in and out system. All right, so this essentially then forms the front cover of a little folder of information about it, which contains a couple of things. One is the measurement templates we have. So all of the engines that we do, we strip and inspect all of the major components, we measure everything, and we compare it to the factory tolerances. In the case of the E-Type, we do so many of these engines that we have a back cover which has all of the dimensions and tolerances of the internals. So this is things like bearing clearances and housing diameters and journal sizes, all that kind of stuff, and things like run out and end float and the kind of things that we need to understand to be executed. Okay, so inside here you'll find a lot of scribblings. This is, for instance, measuring the followers, the tappets.
Okay.
So we measure all the follower diameters, and we compare the worst wear area and the least worn area, so that you can see how much, not only how much wear there's been overall, but how much distortion. So this is what we call barrel wear, where the tops and bottoms of the followers are narrower because of the slight rock that they have, and that the centre of the follower is wider. Prior to doing the rebuild, to understand what the condition of the engine is as it's received, and then we can make recommendations for what machine needs to be executed. This gives us a view, for instance, of whether it's a good idea to machine the tappet guides and replace the tappets. So that kind of thing is there, and again, rods and bores and all of those kind of things. We take all of those, and then for each of the major components, we also have a checklist. So the checklist on this one says things like measuring the end float, removing it from the block, cleaning and numbering the shells, and so on. And we're about halfway down the checklist on this, because this checklist also carries on into the machining and the reassembly process as well. Okay. And so we're about halfway on these kind of things. So the next step on this one that it says is write the machining request. So now we understand what's going on. This is the crankshaft, and this is actually the crankshaft from this. Now we understand what's going on with it, we will then write a machining request for the machine shop to do the machining to our specifications. So we don't just send it off and say, grind that for us, will you? We make sure that we make the request specifically about this engine.
And this is looking fantastic. I mean, so I think you said this has just come back from acid dipping.
So that's right. So I don't know if you remember when it came in, it was looking a bit rough. Yeah. So a lot of external corrosion. We've pulled out all of the core plugs, and as you pull them out, you can see all the sludge and scale that builds up over the years from the coolant. And anything in the coolant settles to the bottom of the block. Yeah, so when you take the core plugs out, you can sort of dip your finger in and pull out something that looks a little bit like silt or mud. So the acid dip process removes everything externally. So that's the old flakes of paint or any external corrosion. But most importantly, it clears out the coolant jacket. That's the real reason we do it. I mean, we could externally clean it quite effectively in order to repaint it, but we can't get inside that. It's quite a long process. It takes about a week in
pickles for a week.
Pickles for about a week.
Wow.
And they flip and rotate and blast it all through and all that kind of stuff several times during that time to make sure that it's not just touching what you can see, it's getting into all the crevices and everything. So essentially it comes back like this, and it just looks like a fresh casting when it returns.
Yeah, it's lovely. So I mean, my non kind of expert eye. I mean, you've done quite a few of these XK engines now, haven't you? And so I'm looking at the state of the bores, and we talked before that you can get crack propagation between the 4.2 bores because
they're quite close together.
That thick, but even so, it looks pretty good condition. This to me,
it's not bad at all. There are none of these cracks which you do typically see. But what I can see from this one is, particularly on this one, for instance, you've got a little tiny bit of liner drop there.
Yes.
So the liner itself is sitting slightly lower than that. So what we would do with this one is to put in top hat liners.
Right.
or stepped liners, one way or the other. You can step them either at the bottom or at the top.
And if you do one, you do them all?
You do one, you do them all, yeah, absolutely.
Okay.
And that process means that, unlike the original liners, which are just a straight-sided sleeve,
Yeah.
and they're pressed in and they just stop, which is what we see here, where you can actually see it's moved a little bit, is we do a step liner, and there are two sorts, one which has a step at the bottom and one which has a step at the top.
Right.
They're much of a muchness. It just depends on the machine shop and the preferences of the people who are machining it. We use Chessman Motorsport. They do a bottom stepped liner for what they do, and they're XK specialists, so that they know these engines, and they're doing them week in, week out, and we really trust the work that they do.
And another thing I look at here is kind of looking at blocks, and I think I've seen it on heads as well. You get a fair bit of corrosion around kind of the holes for the water jacket.
You do.
Through. So these look healthy to me, but what's your...
Yeah, these are perfectly healthy. You can see a little bit of frilliness, but it's just where the gasket line has been sitting, and that will seal perfectly well with a new gasket on it. Particularly on the aluminium cylinder heads, we get a lot of corrosion around those, and sometimes they have to be welded and then slotted back to their original spec.
Is there anything else kind of on kind of initial inspection that
not on the block? We've got a snap stud, which is...
Oh yes, you said the head was a bit tricky to get off.
It was extremely tricky to get off. We managed to snap a stud undoing the cylinder head in the first place.
Right.
Then the cylinder head came up about half an inch and stopped and jammed into place.
Right.
After some proper fighting, we managed to get it off. We ended up cutting two of the studs as well to get it off.
Right. So there's a point at which you just need to draw the line.
You just need to draw the line. It took us a little while to get the head off this one, but obviously because everything has to be reused and preserved, you can't go too mad with ripping it off or being too violent with it. So you have to just take your time, work your way through it. There's a few techniques that we deployed to get it off, and it came off in the end.
Yeah, okay.
And
it's not that anything was wrong as such.
It's quite common. It's just bimetallic corrosion between the steel studs and the aluminium of the cylinder head, and you get corrosion up in those. If you look at these stud holes, you'll see quite clearly that they go down into the cooling jacket.
Yeah.
That means that there can be some seepage past these threads, and that coolant can work its way up the thread because it's got nowhere else to go. Yeah. It can work its way up, creates corrosion, just a tiny little bit of water moisture that comes through over time. Yeah. And unfortunately it creates that corrosion.
Yeah, we've been together for decades, so why would it want to come apart?
Exactly.
One thing you said to me is that this has had a rebuild before.
Yes, indeed.
So
yeah.
There's signs of a previous regrind.
Yeah.
And this is not sure.
This is where the problems begin, because what we found on this one actually is it's had a pretty poor regrind. Okay. So if we'd have had this regrind back from our machine shop, we'd have sent it back and said, sorry, this isn't good enough.
Okay.
I mean, that's not what we get back from our machine shop. We were working them for a long time and they know how to do it properly.
Yes.
If we were to receive this from a machine shop, we would be quite disappointed with this grind, because there's considerable, around about a thou in old money, sort of 0.02 millimeters of out of round. So it means that measuring your side to side and your top to bottom, we're seeing quite a disparity of that. And it isn't down to wear, it's down to grind.
Okay.
Because it isn't what you'd expect, which is the top to bottom is smaller and the side to side is bigger. It's kind of random and all over the place. Okay. Wow. So that's the first thing I would make the observation of. The run out, which is how much, if you put a gauge on the centre and you turn it, how much uppy downy you get, is just in spec. Right. So it's a couple of thou and the spec is a couple of thou. If it was the good old days, if this was a 10-year-old car in the 1970s and somebody wanted to quickly repair it, then they'd throw a set of shells in and off they go and probably never have a problem with it.
Yes, okay.
But we like to do things properly. Yeah. So there's a couple of interesting things about this crank. One is this not very good grind that we've got, and we've got these sort of numbers jumping out at us on the out of round. Yeah. Anything over half a thou of out of round. I mean, if you think that the running clearance in here can be as small as somewhere between a thou and 2 thou of running clearance, half a thou or more of wobble or distortion is changing the way that journal is interacting in its bearing space. Yeah, of course. And you're occupying, a quarter or a third of the space available just in that kind of wobble. Yeah. So we don't really like that, and it can give you an inconsistency. So we want to make this as durable and reliable.
It's never going to get better over time.
And it's not going to get better over time. I mean, one of the things about wear, particularly on bores, is if you've got some sort of taper or some sort of machining disparity like barrel distortion or hourglass distortion from machining processes, that really accelerates the wear on the reciprocating components. So you'll see ring wear and skirt wear as a result of that, just because it's generating more heat and it's moving stuff around more.
So in terms of the kind of the previous less than ideal regrind,
yes,
it's all completely retrievable.
Sure, absolutely. So it's been reground to +10 previously, and we will take it to +20. So that's and when we're talking about 10s and 20s, that's thousandths of an inch.
Yes.
So it's about a quarter of a millimetre. It's between sizes essentially.
Okay.
So we're only removing essentially an eighth of a millimetre from each side of the journal, all the way round, to give you a quarter of a millimetre of smaller.
And how much can they tolerate in terms of +10, +20? When do
plus
you say stop?
+40 is the last available shell that I know of. Although I have heard that they used to be +60 shells available. Not sure that's the case anymore.
Oh, okay, so if we're going to +20 now, then this engine's still got decades.
Three,
of
yeah,
life.
absolutely, yeah.
And
we've still got three regrinds left in it.
Yeah. Okay.
The cranks are not unobtainable either. They're fairly easy to get hold of a crank. I mean, we have, funnily enough, just last week we had a crank that had spun a rod, and it was already on +30, and it couldn't clean up at +40. Unfortunately, it was so that crank is scrap.
Yeah.
But we obtained another one very quickly.
Yeah.
So there's
plenty
of these out, and admittedly, you'll notice that on this here you've got the original number. So that one is 7E13883. And if we look on here, you'll see that the block number.
Oh, that's very nice to know. Okay, so it's on its
original. This is the original crank to the block. So it's matching block, matching crank.
I have to say, I really do love this stand you got here, because it allows you to rotate the whole crank. It's really, really nice.
Well, it really helps us for measuring and checking, inspecting the crankshaft itself.
Yeah, of course.
So you can see across here, you've got these chatter lines from the original machining.
What does chatter actually mean?
So chatter is usually comes from vibration in the grinding stone. So it's an oscillation in the stone that's grinding it, and it creates these little flat spots. Essentially, you're 50-pensing the journal itself.
It's on quite a few of them, isn't it?
Yeah, it's on pretty much all of them actually. It's in the original machining, and that's how it occurs. And then why it shows up in a used crankshaft, for instance, is because the high spots rub off and go shiny, and the dips are darker. Yeah.
So again, this is a symptom from when it was remachined.
This is when it was remachined, so that when it had its first rebuild, it was taken to +10 oversized bearings, and the machine that they've been using has got some wobble on it.
So by comparison, you have this one over here that's not an E-type crank, but we can see here.
This is an Aston Martin V8 crank that's just been freshly reground, and you can see how perfect.
Yeah, it's absolutely lovely.
Those journals are.
So what happens when it comes to actually balancing the whole system? Because obviously these great big journals, it would have been balanced once.
Indeed. Well, you can, if you look here and here, you can see where the factory have removed material.
There's a great. You must have seen it. There's a great period video of Brands Lane.
I have seen
when they
it.
were
Yeah,
doing
it's
this back
lovely,
in the
isn't
day.
it?
It's really, really good to watch.
And you can see these little areas where they've really gone hard. You can see it's actually blue to the crank where they've gone in. And this is the original factory balancing stuff, and they'll have been doing these every couple of minutes. You're balancing another crank.
Yeah.
We do it a bit more carefully than that these days.
Right, okay.
So when we have had the crank fully machined, it's the last stages to have it balanced. We take all of the rotating parts. So in the case of this, there's a couple of sprockets and a couple of pulleys that go on the front.
Yeah.
And the flywheel, and I think we can talk about the flywheel in a minute, but the new flywheel, because I know we're going for a new flywheel on this one, and the new clutch pressure plate.
Okay.
So we assemble the full rotating assembly, and we balance that. So all the parts are balanced individually. Then it's assembled, marked so that it only goes together one way, and then it's balanced up. And of course, material is removed in order to create that balance. And in the case of the crankshaft, that's grinding bits off the webs. And in the case of things like the flywheel and whatever, that's usually just done by drilling holes. Right. So unlike with balancing a wheel and tyre assembly, by adding weights onto it.
Yeah.
When it comes to these, we do the opposite. We take weight off the heavy side rather than adding weights to the light side.
A few weeks ago you sent me a picture of sludge being pulled out of here, and
Sure,
so I hadn't even
absolutely.
realised there was a plug within the crankshaft.
Yeah, so these are access and drilling holes for when the crank's made and built in the factory, and there's drill holes that go through from the mains to the big ends. So you've got diagonal drilling holes that go through and join up these. So they're fed. The oil is fed to the mains through a drilling in the crankshaft to the adjacent big end journal. And in order to do that, of course, they have to drill holes and make some space to do the drilling. And they create these access holes. What happens over time is centrifugal forces going on inside here. You get an amount of very very fine particles, like a silt, comes out, and eventually it goes into a sort of waxy material which slowly blocks your crankshaft.
Oh, okay.
So at a certain point, you can actually get a bearing failures from the fact that you're now starving the crank of oil because it's actually been blocked up with the sludge. All of the cranks we deal with, we take all of the plugs out, we clean it out very thoroughly, and then we use high pressure lance wash to get everything out, and then we clean it off and put the plugs back in.
So at this end of the crank, we've got the notorious crank end seal.
That's right. So you can see on this, it's got a little groove, and it's a spiral groove, and it's called a scroll. Mm-hmm. And essentially, as the crankshaft's turning, the oil is being worked back down this.
Okay, so it's always pushing the oil back into the...
It's always pushing the oil, yeah. So you've got this. So we use this kind of seal. It's called a rope seal. It comes in two halves. You insert one in the block half of a housing and one in the sump half of the housing, as it were.
Yes.
And they go together, create this seal around here. And essentially, they're just wiping the oil from here, and the scroll itself is doing the work of channeling the oil back inwards. This little thing here is a flinger that kind of prevents as much oil getting to the rope seal in the first place. So you've got a couple of lines of defence, and then, however, they do shrink. And of course, what it's all about is the join between these two ends here is where you start to get the leaking. Now we have ways of upgrading to a modern type seal. So this is a larger diameter than the one we'll actually be using. This is actually one from an MGA conversion that we've developed. This is a full lip seal. There's no splits or anything for it to come out. And essentially, if you machine a clean surface onto your crankshaft and put one of these on, that's it. You're done. You've cured your leaks, because this is what modern engines have. It's a very simple solution to an age-old problem. Now, in the case of the E-Type, then you've got to do a bit of work. So firstly, you have to take the rope seal housing and machine it out with square shoulders to insert one of these.
Yeah.
Secondly, you have to remove this flange here.
Yeah, because I was thinking there's no way you get a seal over that and onto there.
No, you won't. I mean, there are split seal alternatives actually, and we do a less expensive version of the one that we're talking about on this, which is a split seal. It's like one of these, but it's got a cut in it, and you split it, you fold it around, and then you put a little bit of silicone on the end of it, and you put the split at the top where it's least likely to leak, and that's basically that's basically where we go with that.
But this is where you attach your flywheel.
Indeed.
So what do you do instead?
So instead, this is machined off, and the original scroll is machined off, and we take it down to a clean metal with a fresh diameter that suits the new seal that we've got. Then we re-drill 9 holes in the end, and we put on a new steel flywheel with 9 holes in it, and a set of ARP bolts which hold the flywheel on.
I can see now why it's such a substantial modification.
It's a substantial modification, yeah. The new flywheel is counterbored for the right size, and it slips over the end to keep it located centrally. Then it's bolted with the 9 ARP bolts, like torqued up quite strongly as well, like 100 foot-pound, something like that.
Right.
And then the whole assembly is balanced, as we discussed before.
Okay, so next on the workbench, we've got one of Audrey's con rods, a piston, which looks as though it's been running a touch on the rich side.
It does, yeah.
And a flywheel. So con rods, you've got them in your report.
Sure.
I think as being relatively healthy. I think.
They are. They're relatively healthy. There's no real signs of abuse on this engine. It's been rebuilt. It's been rebuilt to a reasonable standard. The machining, on the other hand, wasn't that great. So the bores and the crankshaft are both quite badly machined. And that's something we'll be correcting. If we have a look at the conrods, we've got the report here, and it tells us about them. And there's nothing really wrong with these rods. They're in pretty good shape. There's nothing in here. I've got just one amber in the big end measurements, and that is just 5 microns over the max. Now, that's not something that would worry me at all. That's in old money, that's a couple of tenths of a thousandth of an inch. Right. So it's a really, really very, very small number out of round. Not something to cause us any concern. And in fact, the bearing shell itself will compensate for that amount of distortion in the end there, so that could well have been in there from the day one of the factory. The rods themselves do have a bit of surface corrosion on them, so we'll vapor blast the rods, and of course once we've vapor blasted them we will be fully inspecting them visually for any nicks or anything that could be a stress razor, and we can just remove those very gently with a rotary tool.
And they don't get plated or painted or anything?
No, they don't get plated. Vapor blast them, which just gently removes and slightly compresses the surface. You mustn't sandblast rods because that can create little chips and stress razors.
So you'll end up replacing the bolts on the end of the big end here, won't you?
Yeah, we consider the rod bolts and nuts to be consumable items. They just get replaced in the same way as bearings and gaskets and so forth.
And I think you said that you can actually measure not only the amount of wear at the big and little end, but also the amount of twist.
Yeah, that's right. So we look for any distortion or deformation in the rod that's either come from forces or damage or whatever it might be that it's endured, and sometimes we might need to correct that as well. So we have them measured. Essentially, our machine shop will line up the big end, and then they'll measure deviation at the gudgeon pin to see how much twist or bend there is. So it could be bending this way, or it could be relative rotational with the alignment of the big end. Yeah. Gudgeon pin's replaced with the piston, so the piston and pin come as a set.
Will it be necessary to replace these?
It will be, yeah. So again, these have been up and down a few times.
Yeah.
They're not in bad shape actually.
Okay.
Typically, this is quite good. You've got a nice even wear pattern, and there's nothing. There's not. You can see a bit of vertical scoring and some sort of highlights where a little bit of debris has gone up and down.
Because there's a really big skirt on these. I mean, compared to some other pistons I've seen, it's really quite a...
Yeah, there's quite a lot of skirt. I mean, it's a fairly average-looking road piston. Mm-hmm. We don't need to take a lot of weight out. They're fairly slim in the skirts as well. It's not a particularly heavy piston.
Yes, I know. So it doesn't weigh much at all
for its size. And this is just a nice compromise. It'll be a nice quiet piston. It won't be slappy or anything like that. And a fairly good, durable, long-distance piston.
Now, see, as we discussed, I think previously, the amount of dome on this. So this would be an 8-to-1 compression.
Yeah. So you've got two. You've got an 8-to-1 and 9-to-1. Not particularly sensitive to compression ratio. It's not like it's really worth pushing it up to 11-to-1, for instance, and really trying to deal with that. They don't perform a great deal extra with more compression. In the race engines, obviously, that's a bit different, and with the amount of port work and those kind of things that go on, you can push those compression ratios up. But on a road car, it's sensible to stick with 9-to-1, and as long as you're using a decent quality fuel, you're not going to have any problems with that, and you do get a little bit more performance. So we always fit the 9-to-1 pistons.
Oh, okay. Okay, so that will be in effect a kind of going to a slightly higher compression ratio than it was. The new piston comes with the sleeving. Okay.
That's right. Yes. Essentially, what we do is we fit the new sleeves into the block, and then we buy the pistons and have them in our hand.
Yeah.
And then we measure the pistons, the new pistons, and then we bore the block to give the correct clearance to those pistons.
Oh, okay.
So although there are, sort of factory tolerances, and if we have a look on the back of here, we can actually see what the E-type bores, cylinder bore sizes are. For instance, a 4.2 standard bore is 92.075 to 92.103 millimeters.
Right.
So that's the standard factory bore, and if you bought a set of pistons and you bored the block to that, you'd probably be safe.
Yeah.
But what we like to do is be a bit more accurate than that, and we work backwards from the clearance that we want.
Yeah. Okay.
And so we start with the clearance that we know we want. We measure up the new pistons. There can be a fairly sizable variation between a set of 6 pistons.
Yes. Okay.
So we measure all 6, and then we actually size all 6 bores to give you an even clearance across the 6 pistons.
One thing I meant to mention is I can see how you measure the bearing surfaces on the crankshaft.
Yes.
How do you go about measuring these internal dimensions on the big end?
Okay, so we use a bore gauge, which essentially is a spring-loaded gauge, which has a dial indicator on the top of it, so I can show you roughly what that looks like. So we take the bore gauge, we add on to the bore gauge a dial, like this, and turn that on, and then as you can see, as I'm pressing in the little pip on the end, it's moving the size of it. So we put that in, we rock it around, and that gives us the diameter of the internal of there. And of course we have different sizes of these going all the way down. I think we can measure as small as 3 millimeters, something like that, or even slightly less, maybe 2 millimeters.
Oh wow! Okay.
We've got some very, very tiny versions of this.
Yeah.
And we can go all the way up to as big as you'd get on a bore in a classic car engine. We can do up to about 150 millimeters, I think.
Right.
Which would be a 6-inch bore. That would be pretty huge.
Yes.
For a classic. So
this is your measurement set of kits.
This is stuff that we use typically for measuring up our engines. We use decent quality micrometers. These are all Mitutoyo micrometers, all of the same set, and we do actually have a larger one as well in the box, which is the 4 to 5 inch one. So that's about as big as you'd go on a set of pistons, for instance, which would be the sort of largest diameter that you'd want to measure. Yeah,
that Aston block looks like it's got a pretty chunky pistons.
They're up to 106 mil, something like that. So you'd start to go into this range with those ones. We also have other stuff like very accurate scales and those kind of things for measuring and balancing, particularly reciprocating masses. So that's the micrometers, and then in this we've got split ball bore gauges. So these go right down to a very, very tiny bore measurement. You can see they've got a tiny little split in the end, and that's what measures that, and we can calibrate them right down to a very small size. These are calibrating, called setting rings, and those go all the way up to, this would be the biggest one, which is 20 millimeters, and again you use that in there like that to calibrate it, to zero it, and then you can measure stuff. Because
this is way beyond your kind of standard home mechanic set. Let's face it, isn't it?
Sure. Yeah. I mean, there's some expensive kit here, and of course we keep it all calibrated and checked regularly.
And we're in a temperature-controlled room as well. I guess that must play an influence.
You can have a look. It's set to 20 degrees in here, and actually I'm looking at the thermometer behind us. It says 19.9. And so these are bore gauges that go up to that point, and they measure up to with this one we can do up to 150 millimeters.
Right, Roger's just got his slip gauge set out and is going to show me how this works, because I think there's some magic involved.
There's a little bit of magic. So these are gauge blocks. They're essentially a block of metal which is of a known size. So a 40 millimeter one like this is exactly 40 millimeters from side to side. Okay. So what that allows us to do is, for instance, get a micrometer and calibrate that micrometer or zero that micrometer to exactly 40 millimeters.
Yeah.
And that allows us to be very confident in our measurements, that they're very accurate. Now we use good quality metrology equipment here, and it's all calibrated somewhere between plus minus 3 microns of the actual measurement. And of course, when we're talking about machining tolerances of around 10 to 15 microns, it's well worth having it down to that level so that you can accurately say that you're within that window. You have it. What you were mentioning there, the magic involved is that you can ring these together. It's called ringing.
Okay.
And essentially, you take two of the blocks, and you put them together and you twist them, and they're so flat that remains stuck together as if it's magnetized. But it is actually the fact that they are so perfectly flat that they're just sort of held together by magic.
It is. That's mad.
There's probably scientific papers on how it actually works. whether it's the weak nuclear force or something, I don't know. Yeah. It's magic as far as I'm concerned. But I thought that's a pretty cool trick.
Can I just give that a go?
Yeah, sure. Yeah. So what you do is you press the two together.
Okay.
Fairly firmly, and you twist, and then it stays in place. So give that a go, but do it over the bench in case it goes horribly wrong.
Okay, well.
But you can sort of feel how
Oh my word! There's a huge amount of stiction.
it feels like magnets, doesn't it?
It does. There we go. That is amazing.
It's
Magic.
incredible, and I think even the world's greatest scientists are baffled as to how that works.
Brilliant. So that brings us to the flywheel. Now, the flywheel, you tell me this isn't likely to be the original flywheel.
No, it's not likely to be the original flywheel because I can't see an engine number on it, and usually we'd find around the rim, we would find the original engine number stamped into it, and it would be matched to the crankshaft and the block.
Okay. And it looks like there's some fairly significant. It's more than scoring. It's kind of
it's gouged out, hasn't it? So we've got two of these radial grooves, which I think are probably down to the fact that at some point the clutch plate material, the friction material, wore away completely, or possibly even delaminated or fell off or something, and that the clutch was running against the rivets within the clutch plate itself, and that's created these two grooves. Now, they're quite deep, and I know that because we're having a new flywheel on this engine, because we're doing the rear Viton lip seal conversion,
yes,
we won't be reusing this.
The clutch pedal was really heavy and right at the end of the travel for the very limited manoeuvring I did on the car.
So it may well be that this is part of that story.
Right, so here we've got Audrey's head alongside another couple. I see you've got a lovely pumpkin one there. Would that be from an E-Type, or was that...
Yeah, this is an early E-Type. This is this particular one's very, very early E-Type, first couple of weeks of production.
Wow.
As it happens on that one. And then this is a later, but still a 3.8 E-Type.
Okay.
On this. And those are the correct colours.
Yeah, we were just talking about this because this being a 67 car probably should just have a silver head. Oh, see, there's the studs that got
unusual features of a E-Type. They don't normally have this. So this is exactly as the cylinder head was when it was removed.
Yeah.
All we've done is we've stripped it down to access the bits that we want to measure. So on a cylinder head, we would measure the valve guides, and we would measure the tappet guides. Yes. And that's pretty much all we really measure. In terms of visual inspection, we will obviously be looking for instance, corrosion around these slots. And
those look great.
They look good.
Pretty crisp.
They look in really good shape. And when this is skimmed, we'll have a nice fresh surface going on there, and I don't suppose we'll see any problems. Very occasionally, we have had it where we've skimmed a head and it's revealed a pocket of corrosion, or it's revealed something like that. But that's very rare actually, and not something that I'd be particularly concerned with, and it's not something we have a problem fixing anyway if we do find it. The original E-Type valve seats were not hardened,
right?
But they can be run with super unleaded fairly successfully. Lots of people do that, and also with a lead additive that you can put into the tank.
Yeah.
If you're doing the full restoration, it's a really good idea to have those replaced. So have the seats replaced. From that point onwards, then you've got no problem with whatever fuel you're going to be using. You just replace them with a hardened insert. This head hasn't been cleaned or anything, so before we send it away for machining, we fully vapor blast this and bring it all back to a fresh cast appearance, and we get rid of all the carbon build up in the chambers and everywhere like that.
Yeah.
Then it goes away from machining, so the actual working surfaces are replaced and cut fresh, and you really do have a brand new cylinder head. The other thing we do is we pull all of these studs and we just replace them.
Yeah. Okay.
They're about £1 each or something. It's really not worth having the discussion about shall we reuse or electroplate these parts, because they do, particularly on the exhaust side, they do have a bit of a hard life. On the other side, when we look at it from this side, you can see quite clearly that we've got some polishing on the top and bottom of the tappet guide itself, and essentially this is indication that we've got wear from the rocking motion of the camshaft. That can be very easily corrected. We just put in an oversized tappet and machine these tappet bores up to make sure that these are firmly held into the cylinder head, and they do have something of a reputation for falling out, which is unjustified really. They only really do it if they overheat or something like that. But to check that before we machine them, give them a good test, bit of a pull up to a certain torque, and if they don't move, they're in there
Okay, yes. Okay.
So that they are checked prior to machining, so that we don't machine something which is liable to fall out.
So you machine these in situ, they really don't get taken out?
So they're machined, yeah, absolutely. They're machined in situ and just honed up to the next size available.
And it looks like the head's in pretty good condition, but basically once you vapor blast it, then you'll be able to really give it a further inspection.
Absolutely. Well, it'll be fully vapor blasted. Then we'll give it a visual inspection before we send it for machining. We'll write a machining request to ask them to do the work that we want, which we'll agree with you as the customer prior to sending it away. And then from that point onwards, it's with the machine shop to do their magic.
Roger, thank you very much for taking me through all of the constituent parts of Audrey's engine.
Indeed.
And I see you've got a report here for me as well, so thank you
have,
very
yeah.
much.
I mean,
it's a great part of the history to have with resetting this car.
It really does add value to the engine rebuild itself as well, to have all of the details and the proper measurements in there. We quite often receive engines in here which claim to have had a full rebuild, and when we open them up, we don't find that to be the case.
Okay.
Hopefully, customers haven't paid out for work that hasn't been done, but we like to do it properly. But the engine inspection report, it's a great part of the history file of the car, and well worth having it. And the lovely thing about this now is it's our segue into the next phase of the build, where we're going to start machining the parts, restoring the visual appearance, the cosmetic appearance of all the parts, and bringing it all back together as a factory fresh.
Well, I'm so looking forward to seeing it that now I just need to get the rest of the car ready to reattach to the engine too. So looking forward to seeing that, and I'll come down here again because of course I've got to get the carbs rebuilt, and you very kindly said I can come down here and do that, and you can show me what you do as well. So
absolutely, we can help you through that process.
Thank you very much.
Pleasure.
Thank you very much for watching. I hope you've enjoyed that. I've certainly learned a lot from it myself, and I'm really looking forward to seeing when the engine looks something like this one at the end of its rebuild. Please join me again in the next episode.